All right, let's dive into trigonometry and master a really simple trick that lets us model the real world, the vertical shift. Seriously, this is the key to taking those perfect textbook waves and making them fit everything from the temperature outside to the height of a Ferris wheel. So let's get right to it. So you know this classic wave, right? It oscillates perfectly around the x-axis. It's kind of the heart of trigonometry. But think about the real world for just a second. Is this simple wave really enough to describe all the cycles we see around us? Yeah, the answer is a pretty clear no. While it's a perfect starting point, the real world almost never centers itself so neatly around zero. I mean, think about it. The temperature where you live definitely fluctuates, but it cycles around some seasonal average, not 0 degrees. And a rider on a Ferris wheel goes up and down, sure, but their lowest point is still way above the ground. To model this stuff, we've got to be able to move our wave. So how do we move the wave? Well, it's actually pretty easy. We just add one new parameter to our function. It's called the vertical shift, and we usually represent it with the letter d. You can think of d as the key that unlocks all these real-world applications. So what is it exactly? The vertical shift d is just a number we tack on to the end of our function. Its only job is to slide the entire graph straight up or straight down. The shape, the period, the amplitude, none of that changes. It's just a pure vertical slide. And this is where d becomes like the new center of our universe. That midline, the horizontal line the wave bounces around, is now simply y equals d. And from there, the logic is super simple. The highest point is just d times the amplitude, and the lowest point is d minus the amplitude. It's really that straightforward. And hey, this works in reverse too. If you're looking at a graph and you don't have the equation, how do you find d? Simple. The midline is always perfectly in the middle of the highest and lowest points. So you just average the max and min values, and boom, that gives you your vertical shift d. Okay, enough theory. The best way to really get this is to just see it in action. So let's work through a few examples, starting simple and then building our way up. All right, here's our first one. We have a standard cosine wave, but with a +4 tacked onto the end. So what does that do to all our key features? Let's just break it down. First, we identify our parameters. The number added at the end, d, is 4. The amplitude, a, is that invisible 1 that's multiplying the cosine. With those two pieces, the rest is just simple math. The midline is y equals 4, the max is 4 plus 1, which is 5, and the min is 4 minus 1, which is 3. And there it is. We took a standard cosine wave that bounces between -1 and 1, and we just slid the whole thing up. Now it oscillates between 3 and 5, perfectly centered on its new midline at y equals 4. Okay, let's try another one, just to build on this. This time we have a change in amplitude and a vertical shift. Our job is to find the function's range. You know, all the possible y values it can hit. We're going to follow the exact same process. Our amplitude, a, is 3. Our vertical shift, d, is -1. This means our new midline is down at y equals -1. To find the maximum, we just go up 3 from there, which gets us to 2. To find the minimum, we go down 3, which lands us at -4. So no matter what x is, the value of this function is always going to be squished somewhere between -4 and 2. That's its range. Okay, time to work backward. This is a super common type of problem where you aren't given the equation, just the results. We know a wave hits a ceiling at 7 and a floor at 1. Can we figure out its core properties from just that information? Oh, we absolutely can. Let's just think it through. The total height of the wave is the distance from the floor to the ceiling, right? So 7 minus 1 is 6. The amplitude is always half of that total height, so it's 3. And the midline, d, is the point exactly in the middle of 1 and 7. What's the average of 7 and 1? It's 4. So d is 4.
Now, before we go any further, I want to tackle a really common mistake. It is so easy to confuse what the amplitude does with what the vertical shift does. Let's just make sure that that distinction is crystal clear.
You know, the simplest way to remember it is this. Amplitude is the stretch. It grabs the wave from the top and bottom and stretches it vertically, making it taller or shorter. The vertical shift is the slide. It takes the entire wave and just slides it up or down the graph. Stretch, then slide. They are two totally separate steps. Okay, let's put all this knowledge to work on a classic, real-world problem that trigonometry was basically born to solve: the Ferris wheel. So here's our setup. We have this big Ferris wheel. The distance from the center hub to any car is the radius. That's 20 meters. And that center hub itself is hanging out 25 meters in the air. That hub height, the center of the wheel's rotation, is our midline. It's the central value a rider's height is going to oscillate around. So in our function, d is 25. So let's put it all together. The midline, d, is the hub height, 25 meters. The amplitude is the wheel's radius, 20 meters. This means the maximum height is simply 25 plus 20, which is 45 meters. And the minimum height is 25 minus 20, which leaves the rider 5 meters off the ground at their lowest point. See, it just works. We just used the vertical shift to perfectly model the height of a rider on a Ferris wheel. That's the power of D. It grounds our math in reality. So the question I'll leave you with is this: what other cycles in the world around you, from biology to economics, can you now model with this powerful tool? Thanks for watching.